first, and I have 24, 358, 39, 112, 62, 124, 72, 854, 74, 386, 30099, 45, 043, 11169, 8045, 15650, 5451, and 4895. I got a total of 393,186. 393,186. What is the probability selected resident has a travel time of, so probability of 90 or more is 4895 divided by the total, 393,186. And I divide and I get the probability. 4895, I divide by the previous answer. And I got 0.0124. So 1.24%. What is the probability that randomly selected resident will have a travel time less than 90 minutes? So the probability of less than 90 minutes, it's obviously 1 minus the probability of 90 or more. So 1 is the probability of the sample space minus 0.0124. And what do I get? I get a 6, I get a 7, and 9. Or 97.6%. If I am asked, for example, what is the probability that a person, a driver, will drive between 35 and 39 minutes, how do I determine that? So probably 35 through 39. How do I determine the probability of 35 to 39? Can anyone give us the idea? Well, I look at 35 to 39 and I have 11,169 out of the total, which was 393,186, and that's the probability. 11169 over 393,186. Okay, so I got 0.0284. Finally, the last section of chapter 5, in which we're going to talk about independent, non-independent, dependent, and the multiplication rule. So section 5.3, independent or dependent events, and finally the multiplication rule. Okay. Remember when we talked about all my pages are messed up. When we talked about disjoint or mutually exclusive, we were not talking about probabilities. We only talked about whether they have common outcomes or not. Of course, eventually we talked about probabilities, but that's not how we determine whether they are disjoint or not. They have common outcomes, they are not disjoint. They don't have common outcomes, they are disjoint. But here, when it comes to independent and dependent, we do talk about probabilities. That's how we analyze. What is an independent event? Or independent events, better. Two events are independent if their probability of occurrence does not, one probability of occurrence does not affect the other. So I'll say E and F as events are independent if P of E does not affect the probability of F of occurring. And they are dependent if P of A changes P of F. Affects P of F. Changes P of F. So they are not independent. They are dependent. And there are two notes here. One that is very important. These joint events are dependent. They are not independent. And the other note is something that we are going to use later. So this is not for today, but I put it in here. When we take a very small sample from a large finite population, we make the assumption of independence, even though the events are technically dependent. If the sample size is n is no more than 5% of the population size, we assume independence. If it's more, we assume dependence. So I'll come back to this later. I just wanted to put it out there. Okay, so the multiplication rule for independent events. Okay, here's an example for you. $52 cards in a deck, and I select a king. What is the probability of selecting a king? We already calculated. There are 4 kings divided by 52, which is 1 over 13. Now I replace it. Replace the king back to the deck, in the deck of cards. And I'm asking you, what is the probability of selecting a jack? Now, still 4 over 52. I still have 52 cards. I still have 4 jacks in the deck. I still have 1 over 13. K and J are, independent. Notice that because I replaced the king back in the deck, nothing happened. I shuffled, and now I'm asking myself, what is the probability that I select a jack out of the deck? Still 4 over 52. These two events are independent. How come? The fact that on the first trial, I selected a king or I didn't select a king, it doesn't matter. The second trial, when I selected a jack, it didn't matter whether I selected a king the first time or not. So these two events are completely independent. The probability of selecting a jack was not affected by what I selected on the first trial. On the first trial, I selected a king, or maybe not. Nobody cares. The two events are independent. The probability of selecting a jack on the second trial was not affected by the probability of a king on the first trial. Here's the second example now. Same deck of cards. I'm selecting a king again. Yeah, what are the chances? 4 over 52. I do not replace the king back to the deck. What is the probability of selecting a jack now? I still have 4 jacks in the deck. But how many cards are still in the deck? I did not. Yes. See what happened now? The probability of selecting a jack depended on what I selected and the fact that I didn't replace it. So these two events are dependent now, because the probability of selecting a jack was affected by selecting a king, or selecting anything, especially if I didn't replace it, right? So dependent events. This event and this event now are dependent. Okay, So let's look at finally the multiplication rule. So let's start with an example. We have the probability that a randomly selected male survived this year is 0.9986. So the probability is given to us. If we select one, according to the national study, what is the probability that 3 randomly selected males will survive this year? So because events are independent, so the probability of 3 males will survive this year will be the probability of male 1 times the probability of the second one times the probability of the third one. All I have to do is multiply 0.9986 times 0.9986 times 0.9986. Of course, we're not going to write it like this. We're going to write 0.9986 to the third power. Why? Because the events are independent. So the probability of an event to happen is the product of the probabilities of each event. So E1 times probability of E2, and so on and so forth. Take my calculator, 0.9986, power 3, enter. And I get 0.9958, or 99.58%. What is the probability of 20 randomly selected? Okay, so the probability of 20 males. They are independent, so I have the same probability, 0.9986 raised to the 20th power. 0.9986 raised to the 20th power. Get 0.9724. The higher the power, the lower the probability, because now I put more strain on the probability. I want more and more and more people. Okay, so for 1 is 0.9986. For 3 goes down to 0.9958. For 20 it goes even further down to 0.9724. Okay, any questions? Any questions on this?
Nope.
Okay, moving on then. So let's look at the last problem here. So we're going to encounter this in chapter 6 again, compute at least probabilities. We encountered an example here, but we didn't really apply the whole procedure to this. Sorry, my pages are not in order for some reason. So we did encounter something like this, 90 or more minutes. So we determined the probability of 90 or more minutes by dividing 4,895 by the total. But we could have created something like this, and I will come back to this example in a minute. 25 minutes or more, at least 25 minutes. So I'll come back to this in a moment. So at least probabilities. So for example, if I go back to before we do that example, if you remember, we had 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9 numbers in the sample space. So probability of selecting at least 2 will be this probability. It will be the probability of a 2 plus the probability of a 3 plus dot 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 probability of a 9. This is the concept of at least probabilities. At least probabilities. Of course, it will be, because there are 10 and I selected 8, it will be 8 over 10. Or 4 over 5. What if I want probability of selecting at least 6? That would be this. Probability of selecting 6 plus 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 dot dot dot, the probability of selecting a 9. So this will be 4 divided by the total, which will be 2 over 5. So that's the idea of at least probabilities. We're going to use this concept in the next chapter as well. So we have this problem, and then we look back at the one with driving time. The probability that a randomly selected female aged 60 years will survive the year is, so probability for a female is 0.99186. What is the probability that at least one of 500, so n equals 500, one of 500 randomly selected 60-year-old females will die during the course of a year? So the probability, at least one will die. So when we look at the females, between female number 1, they're all numbered till 500. First of all, we should determine the probability. That's one way. We should determine the probability of a complement. We have the probability that the female survives, and the probability of not surviving will be 1 minus the probability of surviving. So 1 minus 0.99186 will be 4, and then 1, and then 8, and then 0, and then 0, and 0. So 1 minus 0.99186. So now, how do I determine the probability that at least one out of 500 will die? So it's 1 or more. So the probability that at least one will die will be 0.00814. The probability that one person will die, but at least means 1 or more, to 500. So 0.00814. And I'm afraid that the calculator cannot give me that number. Because the number is so small. So the probability of that at least one out of 500 randomly selected 60-year-old females will die during the course of the year. Any questions? Any questions? So only because it says it will die, right? So the probability of survival is this. And what is the non-survival probability?
The complement of that.
Yes. Yes. Calculating the probability of a person to die. The probability for survival is very big, right? It's almost 1.
And then you divide that by 500?
It's multiplication. No.
Oh, you multiply.
It's multiplication. So very good question. So we have to multiply. The multiplication rule, right? So here when we selected independent events, so three males, right? So the probability for one male to survive is 0.9986, right? Is that okay? Okay, so then the probability of 2 or 3 people to survive in this case is the product of those. So 0.9986 times 0.9986 times 0.9986, and we got 0.9986 to the third power.
Okay.
Okay, is that better? So we could also, because the calculator cannot give me this number, so the bet maybe, so the probability that at least 1 will die, we can determine as 1 minus the probability. One minus 0.99186 to 500.